In this video, I'd like to work out an example for you that parallels example 9.5 in your book about bicycle gears. I'd like to work out a fairly specific example with numbers where the book's example is a bit general. So let's try this. The front gear on a bike is called the chain ring, and I'm imagining that this chain ring has 38 teeth around it that the chain grabs onto. And the back part of the bike that's attached to the back wheel is called the cog, and it's usually much smaller than the chain ring. In this case, the cog has 18 teeth. And on most bikes, it turns out that the chain, the links are each a half an inch. So that means the teeth are each a half an inch apart. So this chain ring is 38 teeth around, and the cog is 18 teeth around. So what I'd like to try to figure out is, suppose you pedal at a certain cadence. In this case, I just picked 60 times per minute, which is kind of a leisurely rate for pedaling. I might want to ask how fast the rear wheel is spinning. If you pedal, so here's the thing, if you pedal attached to the chain ring 60 times per minute, how fast does the cog spin, given that they're coupled by the chain? I think you'll be able to use the results of this little sample problem too in one of the problems from the back of the book. So here's how you might go about working this out. First, I'd suggest we just find a couple of general things about these, about the chain ring and about the cog. And in fact, the first thing that comes to my mind is to figure out their circumference. Because I do know that when the chain ring goes around once, the chain itself has to move a distance equal to the circumference of the chain ring. So I'll call the chain ring 1, and how about we try to figure out what its circumference is? Well, it's 38 teeth times each tooth is a half an inch. So that would be equal to 19 inches around. And then if we wanted to convert that into centimeters, you could pause the video and do it, or just do it on the fly here. There's 2.54 centimeters in an inch. So that turns out to be 48.3 centimeters around. You could pause the video and see if you can calculate the circumference of the cog. But in any case, the calculation is pretty similar. There's 18 teeth, each a half an inch, which amounts to a 9-inch circumference. And if you convert that to centimeters by multiplying by 2.54, you get 22.9 centimeters. So you might be wondering why we would need the circumference of the chain ring. Well, in the back of my mind, I'm realizing that the connection between the rate that the chain ring spins and the rate that the cog spins is through the tangential velocity. Because these are joined by the chain moves at the same tangential velocity on the chain ring as it does on the cog. And the connection between tangential velocity and a spinning object is through its radius. So why don't we take these circumferences that we just calculated and see if you can calculate the radius, remembering that the circumference of a circle is 2 pi r. So you could calculate this if you want to pause the video, but what's the radius of the chain ring? Well, if I take the circumference, 48.3 centimeters, and divide it by 2 pi, I end up getting 7.67 centimeters. You want to check my math on that? And if I do the same thing for the cog, I take its circumference, which is 22.9 centimeters, and divide it by 2 pi, because the circumference is equal to 2 pi r, I get that it's much smaller, 3.65 centimeters only. So that would be the radius of each of those wheels. Well, chain rings, but doesn't really matter. So again, the connection between the rate that the chain ring spins and the rate that the cog spins is through the tangential velocity. So if I know how fast the chain ring is spinning, and I know the radius of the chain ring, I can find the tangential velocity. I'm thinking of something like this. This one goes around at some speed, angular speed omega 1, and that would wrap the chain along with some tangential speed, and that would wrap this thing around with some different angular velocity omega 2. Now, these angular rotation rates wouldn't be the same because the radii aren't the same, although the tangential velocity is. So from what we know, the cadence of 60 times per minute, how can we figure out omega for the chain ring? Well, 60 times per minute is an omega, but it's not in the right units. So omega 1 is equal to 60 revolutions per minute. But we would really like to get that into radians per second, so we can use our normal dimensional analysis thing to get it. I know that 1 revolution is equal to 2 pi radians. And I also know that 1 minute is equal to 60 seconds. So if you pound that out, oddly enough, the 60s divide out. There's a 2 pi in the numerator. Well, we divided by a 2 pi over here. Because it's 60 times per minute, it turns out to be the same as the circumference, because it goes around 1 circumference in 1 second. Great. Well, omega 2, the rate that the cog spins, has to be equal to its tangential velocity divided by the radius of the wheel that it's connected to. So now we can figure out what that is, because we have the tangential velocity, 48.3 centimeters per second, and we know the radius of the cog. It's a little bit smaller. So if you multiply those out, you end up with 13.2 radians per second. So I wonder if we can put that into context a little bit. Like, how many times around is that? Suppose I want to take 13.2 radians per second and turn it back into revolutions per minute, for example. Or suppose I wanted to figure out how long does it take for the back wheel to go around once. So let's try that first. Let's take the 13.2 radians per second and turn that into revolutions per minute. So this would be the opposite of what we did before. 2 pi radians in 1 revolution. And it turns out to be 2.10 revolutions per minute. No, I'm sorry, I've totally messed that up. How about you calculate this for me? Hold on for a second. Sorry for the delay. All right, I get 126 revolutions per minute. Do you? I promised myself I was doing these in one take, so that's how it's sitting. Could you figure out how long it takes to go around once? Let's see, how would we do that? The angular rotation rate is 13.2 radians per second, but I would like to know the time for 1 revolution. So I would have to get this into revolutions per second and then take the reciprocal of it. So I'm going to leave that for you to figure out. Find the time to rotate once. So anyways, you can follow up this example by looking at example 9.5 in your book. And I also picked out a practice problem that might help you solidify this a little bit.